hello everyone, I am Madeleine Abernot. I'm from the LIAM laboratory in Montpellier in France. And together with the Neuron Consortium, so it's a European consortium, we are working on oscillatory neural networks. And in particular with partners in Paris from AI Emergence, we are working on applications for oscillatory neural networks. And this work is about SIFT-ONN, so SIFT feature detection algorithm employing ONNs for edge detection. And so first, I'm going to describe what are oscillatory neural networks, or ONNs. So oscillatory neural networks take inspiration from the brain oscillations that are used for collective coordinations. And basically, we use the same principle of collective coordination between oscillators to compute. So an oscillatory neural network is like a network of coupled oscillators. So each neuron is an oscillator coupled with like another component that represents like the weight and the synapse of your neural network. And how we compute? We compute by using a phase computing paradigm. So we encode the information in the phase relationship between the oscillators. And there is like a physical phenomenon that exists that says, if you couple two oscillators, they will tend to stabilize in phase. And so if we can configure the coupling between our oscillators, we can choose if they will be in phase or out of phase. And this is basically how we compute. So we can configure our network, the synapses of our network, and then initialize the network like the phases of the oscillators so they can evolve and stabilize to the desired output depending on the coupling. So usually the oscillatory neural networks are used for auto-associative memory or pattern recognition like Hopfield networks. So if you couple all your oscillators together, then you can memorize patterns inside your coupling by using unsupervised Hebbian learning. And so when you input like a corrupted pattern, then it will evolve in time and stabilize to one of the memorized patterns. The issue with this is that it uses a lot of synapses because it's fully connected. And so we are trying to get to go beyond this behavior of oscillatory neural networks. And so to go beyond and to explore different architectures, we developed an implementation of the ONN inside an FPGA. So it's a proof of concept to explore applications. And inside the project, there are other partners that are more developing like devices, emerging devices for oscillatory neural networks and circuits for analog ONNs. But in this case, we use digital implementation, so with digital oscillators and registers as synapses. And so we can see here, like if we want to scale a little bit up the network from like a 15 neuron to 60 neurons, the number of resources required and the number of synapses is increasing a lot. So we are really exploring like to go beyond this. And one solution we found is like to look more into conventional like artificial intelligence with layered architecture. And we started with 2 layers first, and we were able to reproduce like to replace convolutional filters with a 2-layer ONN. So to perform image edge detection. So how is it normally done? You have 2 convolutional filters that scan the image to define like at each point on the image if you have an edge or not. And so we used these 2 convolutional kernels to configure a 2-layer network. So basically you have a first layer with 3x3 that takes information from the image. And you have a second layer with 2 neurons that detects if there is an edge or not. And so we did it with bidirectional connections and feed-forward connections, because using the digital implementation, we can perform feed-forward connection, but for most of the analog implementation, sometimes we are constrained with bidirectional connections. And so looking a little bit at the result of this application, so we were having the same accuracy and precision in terms of image detection as the Sobel algorithm, which is the one we saw with the previous convolutional kernels. And if we compare the 2 solutions, one with the bidirectional and one with the feed-forward, the bidirectional issue is that it takes more time to compute. Why? Because you don't have a fixed input, like the input will evolve in time as well. So it takes more time to compute, and it requires more resources. So if we want to implement like a chip for image edge detection, we need to use like more than 1 ONN. But in this case, we can implement less in parallel than with the feed-forward. And so it takes more time to compute if we consider like a chip for image edge detection. And so another solution to increase the speed and the latency, because it's one issue with image edge detection, is instead of like scanning the image with a stride of 1, you scan the image with a stride of the size of a filter. But then it impacts also the precision, because you can lose like some detection of edges, but then it depends on your application and what you want to do with it. And so we went a little bit beyond this application to see like, can we use this for something else more meaningful than just image edge detection? And this is thanks to the partners, so AI Emergence in Paris, they are developing a robot for safety and security in office. So basically the robot navigates in the office to detect intrusions and water leakage and different things. And so in robotic navigations, feature detection is often used to like detect features in different frames of the image. And by matching the features, you can have the movement of the robot, and it helps for navigation. And so we looked at this problem, and it turns out like the state of the art for robotic application is orb feature detection, because it's really fast. But there are other algorithms like the SIFT, RISC, or others that are like better in precision, but slower. And so they are not used for embedded system because they are too slow. So we wanted to see, can we use like ONN in one of these to maybe speed up the process? Yep. Sorry. And okay. And so the SIFT feature detection algorithm, basically the first step of the SIFT is called a difference of Gaussian. And if you look at the output of a difference of Gaussian, it really resembles like the output of an image edge detection. So we thought like maybe we can just replace this part of the SIFT algorithm with our ONN edge detection, and maybe it will help and speed up the process. So this is what we did. And we showed that, so it's applied for image relocation, but we showed that we were able to speed up the SIFT algorithm using ONN as like an accelerator instead of the difference of Gaussian with the image edge detection, but we also decreased a lot of precision. So this is currently the state of our results with the SIFT-ONN. And next, of course, we would like to improve the results. So maybe we could have the same latency, but with higher accuracy. And to do so, we have one main idea is, so the main difference between the difference of Gaussian and our ONN edge detection is that the ONN gives black and white outputs, what the difference of Gaussian gives like grayscale outputs with like more, like some edges are more important than the others. And so we are exploring how to have output like grayscale output with ONN, which is not so simple. And then we would like also to perform other like tasks, because we focused on image relocation, but with feature detection, there is also other tasks like image occlusion and so on. And then, so this work was like a first work like to go beyond this fully connected architecture with like a 2-layer architecture. And so we would like to explore also multi-layer architecture, and to do so, we are looking into different learning algorithms, because we believe that using the unsupervised Hebbian is not helpful if you want to do really multi-layer like architecture. And so we are looking more into like equilibrium, this kind of learning algorithms. And we hope it will help us to also use ONN for other more complex maybe applications. So thank you for your attention. If you have any question.